All right, hello guys. This is a sample problem on forced convection that involves trial and error. So if we read the given here, we have the specification for the steel pipe, which will allow us to obtain the inner diameter and the outer diameter and the inner diameter for 1 and 1/4 each inch schedule for the steel pipe. We also have the average temperature of the water inside the pipe and also its velocity, and there's a steam outside. Another given is the heat transfer coefficient. So we have the temperature of the bulk fluid inside the pipe, and this is water. Temperature of the bulk fluid outside the pipe, this is steam, and we have the HO, the heat transfer coefficient of the fluid outside. So if we draw the cross section of the pipe here, let's say this is a perfect circle, we have a case of heat transfer through convection from the steam outside at 100 degrees Celsius, passing through the steel pipe by conduction, and then passing through the film here to the bulk fluid here, which is the water, by convection. So we have three resistances. We have three resistances for this heat transfer process. So we have the resistance from the convection, resistance from the conduction, resistance from the convection, and I wrote it here. So we're interested in obtaining Q. For example, we're interested in obtaining Q. The driving force is the difference in temperature between the steam and the water inside at 26.7 degrees Celsius. So that is the driving force. 100 minus 26.7. We have a resistance outside due to convection. H sub O is given. A sub O, basically, it's already given once we check the table for the diameter, outside diameter for this type of pipe. 100, 26.7. And also RO, it's basically from here, minus RI from here. Log mean area, we have a formula for that. Log mean area is A, outside A, inside R outside, R inside. That's the formula for the log mean area. A steel, we need the thermal conductivity for the steel because conduction happens through the steel. The value for the thermal conductivity of the steel is 45. Now AI, we can easily obtain AI if we know the diameter. We can obtain that. And what is unknown is the HI. This is unknown. And in order to obtain HI, we need to use the Nusselt number because Nusselt number is equal to the heat transfer coefficient times the inner diameter. So we're interested in this portion, Ki. This is basically the thermal conductivity of the bulk water inside. That is at 26.7 inner diameter, and the Nusselt number is a function of the Reynolds number and the Prandtl number. Everything, all of this are evaluated at the bulk fluid inside. That is 26.7. Bulk temperature of the bulk fluid inside, which is water. Why 26.7? Because we're interested in obtaining HI, so the perspective should be from the temperature of the bulk water. And also we need to assume the wall temperature here. We know 26.7, that is the bulk temperature of the water, but we don't know the temperature of the wall inside. So we need to assume a value here because it is needed. Most empirical equations, the empirical equations for the Nusselt number requires the knowing the wall temperature. Okay. So for our mm, first trial, um, trial number one, let us assume a temperature for the wall. So let us choose the 26. It should be in between 100 and 26.7. So to make it convenient for me for the first trial, uh, see 26.7 here. I mean, and 100 here. I will choose 65.6 as the wall temperature so that I can easily get the values that I need. So I think it's I need the dynamic viscosity at wall temperature and the Randall's number of the wall. So 65.6, this is the for the first trial, this is the temperature that I choose for the temperature of the wall inside. So immediately I can just copy what is on this table. If we need this one, let's say, okay, 432 times 10 raised to negative 3. So probably we will need this. If it is laminar, I believe we will need the dynamic viscosity at wall temperature. If it's turbulent, we can use the Prandtl number at wall temperature. If you know those empirical equations. So let me erase this. Now I will obtain the variables at the bulk temperature. Actually, I don't need to interpolate because I already choose 26.7. So this is the density, specific heat capacity, 26.7. So these values do not change. Especially we're going to plug okay, diameter u density. Yeah, because average temperature of the water doesn't change. So in our next trial, okay, never mind what I'm saying. You will learn about it later. And equation for Reynolds number, diameter, velocity, density of the bulk fluid, and viscosity of the bulk fluid. It's all here. So by the way, let's look for the inner diameter if the pipe is scheduled if the pipe is 1 inch scheduled for the steel pipe. So the outer diameter is 42.16 millimeter and the inner diameter is 35.05. I'll also write the radius for convenience. Okay. Now let's see what is the Reynolds number. So this should be diameter inside. So yeah, for the Reynolds number, diameter inside, that should be, oh, no. This should be 3505 inner diameter. And the velocity is 1. Okay, this table summarizes the properties of water, by the way. So this is 996.4. And 0.860 times 10 raised to negative 3. There you go. We are at the turbulent region. So we already have a Reynolds number. Our Prandtl number is 5.89. So we can now find an empirical equation for the Nusselt number that allows for this range of Reynolds number and Prandtl number. So after that, we'll be able to get HI, right? And I also forgot to mention what this equation is for. So after we get HI, we have a value for this entire expression. We can equate it to this equation because the Q for the entire process of passing through the three resistances is equal to the Q here. So we can equate the Q for the entire heat transfer from the steam to the water to the Q that we will obtain on this part only. At this part only, the convection here. The Q is equal throughout this process. So we can set T wall unknown. T bug is just 26.7 degrees Celsius. HI, we will use the HI that we will obtain from the Nusselt number. So I found that the Nusselt number that we can use here is the empirical equation from this author, because our Reynolds number is 40,000. It is within this range. Yeah, let's use this number, 4609, and our Prandtl number is 5.89. We can use this equation. Okay. So for this expression, we need Reynolds number. Prandtl number, this is the Prandtl number of the bulk fluid water. 5.89. Okay, we have two variables here, F and K. So it's written here. The R here is just this value. Prandtl number at the bulk, 5.89, and then Prandtl number at the wall. I already obtained it. 2.72. So compute for K and F. Okay, so now we have a value for F to substitute in this equation, also for K. So the Nusselt number, the value here is 27863. HI DI. Okay, so I'm gonna place the DI here. 3505, and then the K is this one, 0.6109. 0.6109. Now we will get HI. 0.56. Okay, now we will be using this entire equation because we now have a value for hi. Yeah, we now have a value for hi. Now, the only if we equate these two expressions for Q, the only unknown here is the temperature of the wall inside. So let's see if we place it here, hi. Okay, so let's see if we place it here, hi is 4856. Yeah, 4856.43. That is the hi. Now the area I is just we can use pi d because the area here is not the cross-sectional area. The area here is the surface area. Yeah, so it should be pi d. This is 35.05. 3505 in meters. So let's say at the 1 meter cross section. Now, for this one, R0, Ri, so remember this 21.08 minus 17.525, basically Ro minus Ri. Okay, it should be in meters. Okay. And so the area should be, if you're going to use radius, yeah, so that's right. 0.02108, 0.017525. Okay. For the K of the steel, it's just 45 watts per meter Kelvin. The long mean area, okay. So for the long mean area, let's see. I compute for it here. So 2 pi, 2 pi L RO RI. So we're choosing at the length 1 meter section of the pipe. And 1209. Okay. Okay. And lastly, HO AO. So the HO is let's see, it's just 10,000. And then this is just pi d outside, d outside, which is 4216 millimeter. Okay, at this 1 meter section of the pipe. So this is the entire Q, 26.7. This is the entire heat transfer from the steam to the bulk water. We can equate it to the heat transfer at the wall at the inner part wherein convection occurs. Okay, so for the inner part, we just copy this expression for the resistance. So basically, this entire expression is Ri resistance mean Ro. Or 85642. Okay, so if you cannot read this, it's just the same as the Ri here. So solve for the T wall, temperature of the wall inside. Okay, the temperature of the wall is 68.51 degrees Celsius. What is our first one? Oh, 65.6, 68.51. We can do one more iteration. This is very near, so we can do another iteration to confirm this. Now, if we do another iteration, the only thing that's going to be affected here is look at this. Reynolds number is not going to be affected because we're using the inner diameter, right? It doesn't change. Velocity doesn't change. Bulk temperature is already fixed. Also, the viscosity, dynamic viscosity at bulk temperature of the water side. So this is still our Reynolds number. Basically, our dog mean area, same. Prandtl's number at bulk temperature is the same. Now, we have a new Prandtl's number because for our second trial, our T wall in is already 68.51. 68.51. So we have a different Prandtl's number for the wall. So I'm going to interpolate for that using 68.51. So just look at the table. It should be in between here. You do interpolation here using the 2-point formula. Okay. So 2.6349. This is the new Prandtl's number, which will, if we, okay, so Reynolds number the same, Prandtl's number at the bulk temperature is the same. So basically, yeah, the same. That's why we can still use this empirical equation. So which variable will be affected? The K, because our new PR wall is 2.63. 2.6349. So we will have a new K wherein we will plug in here 5.89 divided by 2.6349 raised to 0.11. So our new K is okay 1.0925. So far, even the F is not affected because we still have the same Reynolds number. So K, replace this by 1.0925. Let's solve for the new Nusselt number at trial number 2. Okay. So the new Nusselt number is somewhere near. Okay. Now we can get the new H. 617. Okay. 4873, and this is 46. Now, 4873.46. Okay, so we will still use this equation. This time, plug it here, the new value for h, and then plug it here, the new value for h. Yeah, now let's solve for the T-wall in for the second trial. Should be somewhere near. Okay, so this time it's 68.45. So somewhere there. So you can probably stop the iteration here, or you can do the third trial and error. But for now, we can assume that the temperature is 68.5 degrees Celsius, the wall temperature, and the heat transfer coefficient at the for the water inside is somewhere around this value. So yeah, approximately 4,870. So there you go. That is just one version of trial and error for forced convection. And there's actually another one wherein a mass flow rate is involved. But for now, this is the scope of this video. So I hope you learned something. If you have any questions, please comment down below. So with that, thank you for watching. Have a good day.